And the other one,
Set cover?
set cover. Yeah. Vertex cover. I'm not going to write the definition again. We wrote it last time. The definition of each problem. C, D, and E. Okay. And set cover. So in vertex cover, we are given a graph, undirected graph, with edge and vertices. And the question is, how can we cover all the edges in the graph using the minimum number of vertices? Using the minimum number of vertices, how can we cover all the edges in the graph? Clearly you would like to use vertices that are that have higher degrees or more edges incident on them. So the vertex with the highest degree here is C. It has 4 edges incident on it, so it can cover 4 edges for us. So we will pick it. Of course, here I'm just what I'm just describing could be a greedy algorithm for this problem, and we know that this is an NP-complete problem. So a greedy algorithm is not going to solve it. It's not going to solve all instances. It's not going to succeed in all cases. So in fact, it will succeed here because the obvious choice is C with 4 edges. Then you need to cover this edge, so you can cover it with either A or B. So the edges in this graph can be covered using 2 vertices. This is the optimal solution. Okay. Now, how do we define the decision version of the problem? How do we recast this problem as a decision problem? So when we recast a problem, an optimization problem, as a decision problem, we look at what? We look at the quantity that we are trying to minimize. What's the quantity that we are trying to minimize here? Number of vertices. Then the decision version of the problem is the number of vertices has to meet a certain target. So we're given a graph and we're given a certain target T, and the decision problem is deciding whether we can cover all edges using T vertices or less, or whether T vertices are sufficient for covering all edges. So that's the decision version of the problem. We wrote it last time. Okay. Now on the other problem here, the set cover problem, we have a set 2, 3, 5, 9, and we have some subsets of this set. This is a subset. This is another subset. This is a third subset. And this is a fourth subset. And we're given the set. This is the set. The question is, out of these subsets, find a minimum number of subsets that will cover all the elements in the original set. So we'd like to cover 2, 3, 5, and 9. So in this case, we can probably do it with this 3, 2, 9, because it covers, this can cover 3. So this covers 3, 2, and 9. And then we will need a set that covers 5. We are left with 5 only. So we can use this or this. The optimal solution is not unique. So in this case, we can cover the set using 2 subsets. And again, the optimal solution is 2 subsets can cover the original set. Now, what's the decision version of this problem?
Can 2 subsets cover the original set? Or can X amount of
Well, not 2, but T, in general, T, or X subsets. So we're given a set and n subsets of that set, and we are given a certain target call it T or X or whatever. And the question is, can we cover the original set using T or less subsets? Okay. Whenever you need to recast an optimization problem into a decision problem, look for the quantity that you are trying to minimize or maximize, and set a target, or find recast the problem as finding a value for that quantity that you are trying to minimize or maximize that meets a certain target. Okay, so these are the two problems. Now the exercise is assuming that vertex cover is known to be NP-complete. Prove that set cover is NP-complete.
And you mean the decision form of both of these?
Yes, we always work with the decision form because only the decision form can be NP-complete. The optimization form will be NP-hard, right? Only the decision form can be NP-complete. So yes, it's implied always that we are referring to the decision form of the problem. So step number one is what? Showing that
Validity?
yeah, that it's verifiable, that set cover is verifiable in polynomial time. Set cover is verifiable in polynomial time. What does this mean in this case? How can you verify set cover in polynomial time? So verify it means someone is giving you a proposed solution. What will that proposed solution look like? What will be the proposed solution in this case? A number of subsets. So someone will give you, for this set, someone will give you some subsets like S1 and S2. So how would you verify that this is correct or not? Just take the union. If the union gives the original set, then it's correct. If the union does not give the original set, then it's incorrect. Okay, so you have to verify first that it's one of the given subsets, and then you verify that their union gives you the original set. If it does, then the answer is yes. If not, if it does not cover the original set, then it's an incorrect solution. Now we need a reduction. We need a reduction from vertex cover to set cover, or set cover to vertex cover.
We need to reduce vertex cover to set cover.
Yeah, exactly. And a reduction from vertex cover to set cover. So we assume that we have a solver for set cover. You always assume that you have a solver for the problem that you are trying to prove NP-complete. And this solver for set cover is going to take the set, and it's going to take the target, and it's going to take a bunch of subsets, S1, S2, through Sk or N. So now, how can we use this to solve vertex cover? So it's always a good idea to try with an example first. See if you can, given this example of vertex cover, of course, an example is not sufficient, but it will give you a very good insight. How can we reduce this problem, finding the minimum number of vertices that will cover all the edges? How can we use a set cover solver to solve this? So in set cover, elements are covered by subsets. So here elements are covered by subsets. And here edges are covered by what?
Nodes.
By vertices. Edges are covered by vertices. Here, elements are covered by subsets. So I need to somehow map edges to elements and vertices to subsets. Okay, so edges to elements, I can define the set S as the set of all vertices. So my set S is the set of all vertices, which is vertex. Let's look at AC, AB, AC, or sorry, AB, let's do it in a specific order. AB, AC, then B. BA is already there. It's an undirected graph. So BA is there, so we only need BC. So this is the set of edges. BC, CD, CE, and D, well, CD is covered, and that's it. So these are the, we have five edges. So these are the 5 edges. So this is the complete set. Now, what's the subset? What's the subset that corresponds to vertex A? Yeah. Well, the edges that it covers. So vertex A covers edges AB and AC. So it's going to be AB and AC. So these are the edges that are covered by vertex A. What are the edges that are covered by vertex B?
AB and BC.
AB and BC. What are the edges that are covered by vertex C? AB, AC, BC, CD, and CE. So for each vertex has a subset of the edges that it covers. And SD is the set of vertices that are covered by D, and that's only CD. And SE, you have the set of vertices that are covered by E, and that's CE. Okay. So do you see the mapping from vertex cover to set cover?
The minimum.
Okay. So this is how we map the problem. Now, we feed this, we input this into a subset solver, and we give it a target T. So the target is going to be the same. So here, if we are looking for T equals 2, then the number of subsets is equal to the number of vertices that are needed to cover the edges. So if the subset solver, if the set cover solver can find 2 subsets to cover the original set, then it has found 2 vertices to cover all the edges in the graph. If the set cover solver manages to find 2 subsets that will cover the original set, this means that it has found 2 vertices that can cover the original, the 2 vertices that cover the edges in the graph. Because each element here is an edge and each subset is a vertex. Element is an edge and each subset is a vertex. So basically the mapping, we can just describe it easily. We can describe the mapping. How to reducing any instance of vertex cover into an instance of set cover. First of all, let S be the set of edges, or given a graph G, let S be the set of edges E. Okay? And then for each vertex, let's call it U, create a subset S sub U that consists of all the edges that are covered by U. For each vertex U, create a subset SU that consists of all the edges that are covered by U. Then, and so the targets are the same. The target T of the vertex cover problem will be the target for the subset for the set cover instance. So the target is the same. The complete set is the set of edges. The subsets are, for each vertex, there is a subset that has the edges that are incident on that vertex. And the target T for the given vertex cover instance, we are given a vertex cover instance with a T, so we just use the same T for the set cover. So S can be covered by T subsets if and only if G can be covered, the edges in E can be covered by or using T vertices. Using T vertices. So if S can be covered using T subsets, then E can be covered using T vertices. Okay? So now I think we have enough NP-completeness examples. We have done Hamiltonian cycle to TSP. We have done subset sum and set partition. And we have done this example. So now this should give you a good idea about NP-completeness reductions. Okay? So now the next topic, we will just define a number of important NP-complete problems that you should know. You should be aware of because they have many applications, and as we will see in the algorithm usage examples, they arise in different applications. Okay. So the first NP-complete problem is a problem that we are familiar with. We have seen before, which is the graph coloring problem. So we have seen the graph coloring problem. Graph coloring. So graph coloring, I give you a graph. Okay, and the question is, color the vertices of the graph such that adjacent vertices have different colors. If two vertices are adjacent, so there is an edge that connects them, then you have to use different colors. You cannot use the same color. Okay, so for example, we can color A red, then B and D cannot be red, but C can be red, because C is not adjacent to A. Then B and D, we can use the same color for B and D. We can use blue. So in this case, we managed to cover all the vertices using two colors. So this graph is two colorable. Two colorable. Or the chromatic number of this graph is 2. Chromatic number equals 2. Now a similar graph that cannot be colored using two colors. If we just add one more edge, then we can no longer color it using two colors. We have to use three colors in this case. So if we try, this is red, and this is blue, okay. But now, C cannot be red or blue, because C is adjacent to both A and B. So we need a different color. Okay, so then in this case, we will just color C with a third color, like green. And then D, what can we use for D? Yeah, blue. We can use blue. Of course, whenever we give a small example like this, the problems look easy. But these are NP-complete problems. So think of a graph that consists of thousands of vertices and edges, and you're writing a program that reads that graph as an adjacency list. And now you have experience with this because you have worked on assignment 5. So you have a graph that consists of thousands of vertices and edges, and you would like to find the minimum number of colors that are needed to cover the vertices such that adjacent vertices have different colors. This is a hard problem. Nobody knows how to solve this in polynomial time. Okay, no polynomial time algorithm exists for this problem.
We went over this in compilers with optimizing register use.
Okay, so that's a good question. Yeah, so this is definitely related to register allocation in compilers. So what do you think compilers do in this case?
That's approximate.
Yeah, so they use, they use approximate algorithms or greedy algorithms that are not guaranteed to give the optimal solution. So they will not always produce the optimal solution, but hopefully if the algorithm is good enough, then it will be close to optimal most of the time. So that's what you can hope for, when you handle an NP-complete problem in practice. In fact, the register allocation problem in compilers is much more complicated than this. So there are many different considerations. So this is a simplification of the register allocation problem. Graph coloring is just a simplification of the register allocation problem in compilers, but compilers do solve it using algorithms that are not guaranteed to give you the optimal solution. Okay, so with these problems, nobody knows how to solve this problem. Nobody knows an algorithm a polynomial time algorithm that can solve all instances exactly. Now, this is interesting because we have seen the interval graph coloring problem. What's the relation between the interval graph coloring and this problem and graph coloring in general? So interval graph coloring is a special case of the general graph coloring problem. Interval graph coloring, you can represent an interval graph coloring instance using a graph. And we did that. In fact, when we studied the interval graph coloring problem, we represented it as a graph. But this is a special case in which the conflicts that are, that the edges in the graph represent, these conflicts in the interval graph coloring problem come from interval overlapping. So here the cause of the conflict or conflicts are caused by interval overlapping. Now this is a special case. So there is a special cause of the conflicts. And we managed to solve this problem using a greedy algorithm in n log n time. So in fact, this is a very easy special case of the general graph coloring problem. So this is interesting because it's not uncommon for an NP-complete problem to have a special case that can be solved in polynomial time. And this is just one example. So this is the general NP-complete problem. And this is a special case in which the conflicts or each edge in the graph corresponds to overlapping between two intervals. Remember, in our case, the vertices represent activities. And if there is an edge between two vertices, this means that these two activities overlap in time. Okay, so this is a special case that can be solved in polynomial time. And this is not uncommon. Any questions on this concept? Okay. Another interesting problem is the Clique problem. The Clique problem, you are given a graph. I give you a graph like this. And the question is, find the largest complete subgraph. Find the largest complete subgraph. In this case, where is the largest complete subgraph?
Triangle.
Oh yeah, triangle. We cannot find anything greater than that triangle. So this is the largest complete subgraph. We cannot find a complete subgraph with 4 vertices because these 4 vertices are not fully connected. Right? If I add these 2 edges, then the clique in this case becomes the square or the rectangle. If I add these 2 edges, then this becomes the largest subgraph. But without these edges, the largest subgraph is the triangle. Okay? Okay, now there is a relation between clique and graph coloring. So if a graph has a clique of size 3. So this graph has a clique of size 3, right? Which is the triangle. What does this mean?
We need more colors too.
We need how many colors? Well, if we have a clique of size 3, then we know that the number of colors that are needed is at least 3. Yeah. Because if you have a complete subgraph of size 3, then these 3 are all connected, or they form a complete graph. There is an edge from any one of them to the other, which means that each one of them has to have a different color, which implies that if you have a clique of size 3, then you cannot cover the graph using less than 3 colors. Okay. So if a graph has a clique of size k, then you need at least k colors to color the graph. Of course, it could be greater than k. At least k. Okay. The third problem that I wanted to mention is a special form of the formula satisfiability problem. Formula remember the formula satisfiability, you are given a logical formula, and the question is there a satisfying assignment? Can you find an assignment of the logical variable such that the formula evaluates to true? So that's formula satisfiability. Now there is a special form of it, which is the 3 conjunctive normal form. So this stands for conjunctive normal form. The 3 conjunctive normal form, where the formula has to be in a special form, where there is a number of clauses that are related by ands, and within each clause you have 3 literals. So you can have x1 or not x3 or x2, and here x4 or x5 or x6. Here you can have x3 or not x2 or not x1. So this is what we call the 3 conjunctive normal form, where you have, this is called a clause, and each one of these is called a literal. So we have, each clause consists of 3 literals related by the or operator. Now, why is this interesting? It's interesting because even though this is a special case of the general formula satisfiability problem, this is still NP-complete. This is still NP-complete. Now, this is helpful. This can be useful because when you try to prove a problem as NP-complete, you need a reduction from a known problem to the problem that you are trying to prove. And if you have an easier or simpler known problem, that will help you. That will make the proof easier. So working with this 3 conjunctive normal form is easier than working with the general formula satisfiability, or a general formula with no restrictions. So this is still NP-complete, so even though this is a special case. Okay, so this is the clique problem. So the last problem is going to be the graph isomorphism problem. So does anyone know what we mean by isomorphic subgraphs or isomorphic graphs? So isomorphic graphs are graphs that are the same but with different names, basically. So this graph with the so this graph and this graph and you just give different names like A, B, C, D. Or you don't have to use the same letters even. This could be A, B, C, E. Doesn't have to be. It's basically two graphs are isomorphic if they are the same shape, the same graph, but with different vertex names. Okay, so you can do a mapping. If two graphs are isomorphic, you can map from one graph to another. So in this case, you can map the E to the A, and you can map the C to the B, and you can map the B to the C, and the A to the D. So if you can come up with a mapping between the vertices, the graph will be isomorphic. So graphs that look the same. Again, this is isomorphic graphs is not NP-complete, but what is NP-complete is the isomorphic subgraph problem. So subgraph isomorphism problem given a graph or G and a graph G prime, determine if G is isomorphic to a subgraph of G. So what does it mean? It means that, well, let's use this. So if this is G, if this is G, and this is G prime. So is G prime isomorphic to a subgraph of G?
Yes.
Yeah. So basically there is a subgraph of G that looks like G prime. So the answer is for this is yes. Even if you give it this, the answer is yes, because it does have a rectangle. But if you give it a graph like this, the answer is no. It doesn't have a subgraph that looks like this. Okay, so I give you two graphs, basically searching for a graph within another graph. Can you find this graph in this graph? So if you can find this graph in this graph, then this graph is isomorphic to a subgraph of this. Now this is an NP-complete problem.